안녕하세요. Good morning. 네, 안녕하세요. Good morning.
Recording in progress.
All right, yeah, I was actually muting myself. Sorry about that. All right, I think we can get started. So, welcome to week 11 of AI504. And today it's Transformers. So, I guess this is probably the most important class of all the all the classes that we'll have in this semester. So, modern deep learning and AI and whatnot, like like Sora or ChatGPT or like the AlphaFold and whatnot, they are all built upon Transformer. Like one, at least there's like the component there is a component that runs on Transformer. ChatGPT is entirely Transformer. I guess Sora is also entirely Transformer, I guess. Um, and AlphaFold is like a variant of Transformer. So basically, you can say that everything runs on Transformer these days. So probably this is the single most important class that you'll have. So and everything that'll come after this, which is BERT and GPT and multimodal, they're also built upon Transformer. So if you don't understand this course, you will have a lot of problem for project 2 and 3. So so this is how we'll proceed today. So we'll look at the high level idea of transformer and then specifically look at self-attention and then talk about positional encoding for a brief moment and then talk about the sequence to sequence transformer, which is actually the original transformer. So what is a transformer? Transformer was designed for translation. So it came out in 2017 by a team from Google. So it was called Attention is All You Need. So there was a language team in Google that was trying to develop a new model for translation, machine translation. And before this came out, people use RNN, like especially LSTM or GRU. So we've learned that last week, right? So we learned how to do machine translation with LSTM or GRU, both on the encoder and the decoder, right? So last week we saw encoder was on RNN, decoder was on RNN, and then you could train with an attention on top of it to do machine translation, right? So it's the same thing. It's just that inside encoder and decoder, instead of using RNN, we're using something called transformers. Well, I mean, there are two versions of transformer. There's an encoder version and there's a decoder version. So inside the encoder, we're using 6 layers of encoders. And inside the decoder, we're using 6 layers of decoders. So unlike RNN, where we only use a single layer RNN for encoder and decoder, here we're using 6 layers of the same encoder blocks and 6 blocks of same decoder component, right? So that's the high level idea. So we'll first focus on the encoder. So encoder is a little bit easier. Do we have the encoder and decoder? Not yet. Okay, so encoder is a little bit easier architecturally, but it's more or less the same. Decoder and encoder, they're more or less the same. So we'll look at just one block of encoder, which looks like this. So you put words in. So if it's a French to English translation, then you put French words into the encoder. And then there's like five more, like there's 1, 2, 3. There are like 5 more layers on top of this. So inside a single encoder block, there is something called self-attention layer. And then what self-attention layer does is it accepts it accepts a set of word embedding or a sequence of word embeddings, and then it outputs the same number of tokens. So if it accepts 3 tokens, it'll produce 3 tokens. And you can see the colors have changed. So there's something going on inside the self-attention. So given 3 French words in this case, there's something going on inside self-attention, and then it'll generate or produce 3 corresponding tokens. And then this will again be processed by a feed-forward layer or FFN layer. And then after that, there will be the same number of tokens outside. And then this will be fed, the same number of tokens here will be fed into the next layers of encoder, right? And the same thing will happen for 6 times. And yeah, if you look at the feed-forward layer, FFN layer first, it's not that there is a gigantic feed-forward layer that accepts that, processes 3 tokens at the same time. It's just that there's one feed-forward layer, there's one FFN that just independently is applied to each token. So in this case, the token number has changed to 2. So sorry about that. There were 3, now there are 2, but just, you can just follow along. So if there are 2 tokens, then you just apply the same FFN 2 times independently to each Z's here, which are the output of the self-attention layer. So FFN layer is pretty much easy. It's just FFN. And if you blow it up a little, if you expand a little bit, the actual architecture is like this. So there's 2 incoming tokens, and then there's something called positional encoding, but we'll talk about this later, right? There's a separate chapter for this. So instead of having self-attention and then feed forward, there's actually something called add and normalize and add and normalize. So there is a residual connection between in and output of self-attention. So you can see the dots here, right? So there's a residual connection, just like the resonant, there's a residual connection that connects between the input and the output of the self-attention layer. And then there's a layer normalization. We talked about the batch normalization during the CNN class, right? So instead of using batch normalization, we use layer normalization here. So there's a residual plus layer norm. So these and also these are there to help the training process. It's not functionally like making any difference, just like feed for like this or this, because they're actually making differences in the token embeddings, right? Their values will change before and after the self-attention and before and after the feed forward. But add and normalize are just there to help the training process. You know how batch normalization was to deal with the internal covariate shift, right? Just to help with the training process. And also ResNet, residual connection, was to help the training process, right? You just had to learn the residuals by connecting between the input and the output of the layer, right? So these are there to help the training process. So you just focus on the self-attention and feed-forward. And feed-forward is the same thing. It's just fully connected network, the multi-layer perceptron that we talked about in the 4th or the 5th class, right? So all you need to newly learn is self-attention here. So that's what we're going to do. We're going to learn self-attention first, and then talk about positional encoding later, separately. Yeah, visually speaking, let's assume there are 2 tokens coming into your encoder. Then they will be slightly transformed due to the positional encoding, which we'll talk about later. So you can see the color has changed a little bit from the dark green to a light green, right? And then inside self-attention, something happens with these 2, X1 and X2, and then self-attention layer produces Z1 and Z2. And there's a plus here, which is the residual connection, right? So there's X and Z. You connect between the 2. So there's a plus here. And then after you do the residual connection, you apply layer norm. Then your Z's have changed colors a little bit. This is like light pink, this is dark pink. And then feed forward network, FFN is applied independently on both Z1 and Z2. And then you do the same add and normalize. And then finally, something like, like R1 and R2 are produced from this encoder block number 1. And then the same thing will happen in encoder block number 2, number 3, number 4, 5, 6, right? So it's all rinse and repeat. All right. So far, any question? We're going to talk about self-attention now. So it's relatively easy to implement, actually. You're going to implement this Thursday because, and I say it's relatively easy because all you need to do is just define one block and then just copy paste it 6 times, right? You just run a for loop over for loop with iteration, it's like 6 iterations over a for loop. And these are like super easy to implement. You just need to learn how to implement self-attention, right? So what is self-attention? So as I said, the whole idea of the transformer and the self-attention came out in 2017 by a language team in Google. And the whole idea is to handle sequences without the RNN architecture, using only attention. So there's a little bit of like a assumed backstory here. So if you use RNN, like let's draw it here. If you use RNN for like English to French, right? If you use RNN to perform translation, like sequence in a sequence to sequence manner, you have to input the English words one at a time, because RNN architecturally has to accept one token at a time. You cannot accept all tokens at the same time in batch process, right? If there are 5 words, you have to run for loop 5 times. So that's how it is, RNN. And that is why RNN is inherently a sequence model, because if you feed one word at a time, then internally RNN, by updating its hidden layer from H1, H2, H3, it inherently understands the sequence that it was given, the sequence of tokens given to it, right? And the same thing on the decoder side as well, because you have something going on inside the decoder, the French words that it predicted, right? So again, the decoder also has to accept and produce one word at a time. So if this is like 5 words, if this is 6 word, then it means that you have to run the for loop like 11 times. So if it's just like short sentences, like if it's just a single sentence translation, that's not a big problem. But if you are trying to translate the entire document, which consists of like 100 words or 200 words or 500 words, then it means you have to run like 10,000 time for loop, which takes a lot of time, right? And Google is not just serving one person, it's serving at least 1 billion, 2 billion people all over the world. So they are not really liking this kind of this limitation, this constraint that where you have to run for loop every single time. So what they thought about is, well, we have a lot of GPUs, so how can we make a new architecture that can replace RNN, still do translation, and take advantage of the parallel processing power of GPU? So that's where self-attention came out. So instead of using RNN, the for loop architecture, let's use only attentions to handle sequences in a batch manner. So the way they do it is that, as you can see here, in order to actually tell the model that this is actually a sequence, not a. So if you feed this into an MLP, it's not much of much of a sequence handler, because MLP can only handle the fixed number of input dimension, the static input dimension. But if we're trying to handle sequences, the sequence size can vary. That's what we talked about in the RNN class. Unlike the CNN, RNN is there to handle variable length sequences, right? So that has to still hold. And again, on top of that, we don't want to use for loops. So the way we do about it is, if we're given 6 tokens, like 1, 2, 3, 4, 5, 6 token input, then we use attention so that I can attend to like going to movies end. Like, I is giving attention to its neighbors. So there's like on the right side, and then there's going 2 steps to the right side. There's 3 steps to the right side in the perspective of the eye here. And you do the same thing with like. So like is now the main character. We're in the perspective of like. In like's eye, there's I on the left side. There's going on the right side. Two steps to the right side. movie is 3 steps to the right side, and the termination symbol 4 steps to the right side. And then you do the same thing with going to movies. So every single time, one token becomes the main character, and then it looks at the neighbor, its neighbor, and see what's there. So that's how we assume that the model will be able to tell that this is actually a sequence, you know. So that's the whole idea. So a little bit of like mathematically speaking, the way we do it is, if you let's focus on this first, these blocks. So if you look at the first matrix, this is something called attention matrix. This is or attention distribution, attention matrix, whatever you call it. The first row is what I, let's write it down. In the perspective of I looks at itself. So this is also I like going to movies, termination symbol. I like going to movies, termination symbol. So in the eyes, in the perspective of I, it looks at itself, and the compatibility or the affinity is 50%, or you can say that the attention strength is 50%. Looks at like this, looks at like, the affinity or the attention strength is 10%. And then it's 0% for going, and 20% for two, and 20% for movies, and 0% for, the end termination symbol. Like this is just an example. I'm not saying this will happen. I'm just an example. Like this could be a proper attention distribution from I to its neighbors, and also including self. So this will sum to 1, right? Same thing with like. So this is like's turn. Like looks at itself, and the attention strength is 60%. Likes looks at I, and then the strength is 20%, 20%, and 0% all the other. So now again, this is sum to 1. And the same thing here, right? And then this is our attention matrix. You have this attention matrix, and then you multiply it. You multiply it to the word embeddings or the token embeddings. So this is a proper I embedding, like embedding, going embedding. You can think of this as 256 dimension, something like that. So this is obviously 6 by 6. This is 6 by 6. You can think of this as 256 embedding. You multiply it, then what you get is this. So the first row with the word embeddings, you do an inner product between the two, or weighted sum, more like this is like a weighted sum between the two, then you get this. You do a weighted sum here, and then you get this, and then here you get this, and yada yada yada, right? And if you look at the internal of this new embedding, like if this was 256, this is 256, right? If you look at the inside, before the multiplication, it was 100% I here, but now it's only 50% I, 10% like, 20% two, and 20% movies. It was 100% like here, but now it's only 60% like, 20% I, and 20% movies. So you see what's happening here. You are actually mixing things up. So before it was 100%, but now there are other stuff inside. And before it was 100% like, but there are now other stuff inside. So what's happening here is it's contextualizing. So this new embedding is actually holding the context of this sentence where I is the main character. Now, and this embedding is now holding the context of this sentence where like is the main character. So you're like tainting the identity. You're like mixing the identity a little bit. So where you have, so this formula or this equation comes here where this is called the QK. Well, I can write it down. QKV operation. And this attention matrix is this part. So this part. And V is the word embeddings. And then the output is probably this. So everything about the self-attention is about the QK. And then V is just there to multiply. The V is just it's like a vessel that you put you contain, you like hold the embedding information of each tokens. So self-attention, the essence of self-attention lies in with something called QK, like this part, and we'll look at this from here. Question from Namho. I understand the representation of the attention matrix, but when a token is compared against itself, why does the attention strength vary? Well, you'll see here. So we'll actually look at one step at a time, like how we can derive the attention matrix with the Q and K and well, I mean V as well. So generating queries, keys, and values. So QKV this is query, this is key, this is value. So you can think of this as like a database lookup operation. When you have a database or like a key value storage, like Tokyo cabinet or Kyoto cabinet, like that kind of stuff, if you're familiar with that, QKV is you have a query, you have something to ask against the database or the key value storage, and then the key value storage will have all the keys, so you can match your query with the keys. And then if there's a match, you retrieve the value, right? That's how database or the key value storages works. It's just like that. So there's a starting embedding. So this looks like a 4-dimensional input, but this is probably actually like 256 or 128, something like that. But let's assume this is 4-dimensional. So there are two tokens going into your self-attention, right? There are two tokens coming in, and then you have trainable matrices, WQ, K, and V. So these are trainable matrices. And this is 4-dimension. This is 4 by 3. So when you multiply x1 to this, you get q1 because this is Q matrix. When you multiply x2 to WQ, you get q2. When you multiply this and this, you get here, this here, here, and then this here, here, comes here, here. You see what's happening, right? So you have queries, keys, and values ready for these two tokens. You have Q1, Q2, K1, K2, V1, V2. What happens next is you calculate, well, first of all, this is thinking's turn. This is X1's turn. X1 is the main character. So X1 asks the question to the storage or the database. So we're using Q1. We are using Q1 to ask the question from the perspective of X1. So we use Q1, and then it calculates the affinity or the compatibility between itself, Q1, and all the tokens there, so including itself. So Q1 and K1, and Q1 and K2. So Q1 and K1, you do an inner product between the two, which results in 112, some scalar value. You do an inner product between Q1 and K2, and then you get 96 points, some scalar value. And then you do a little bit of normalization because you do a little bit like a divide by 8. And you get 14 and 20. So what's happening here is, if this was, in reality, I think this was 64-dimension. That is, so you have divide by 8, which is square of D, right? Square of D. So dk is the dimensionality of the key value, I mean the key vector. And this is 64 in the actual paper. The attention is all you need paper. This was 64. So you do a square root of 64, you get 8. So you divide 112 by 8, you divide 96 by 8, and then you get 14 and 12. So why do we do this? Why do we do this? The reason that we do this is if you don't normalize, if you don't divide by some value that is proportional to the vector size of the key vector size, then your output, your inner product can become arbitrarily large. If you use, like, instead of using 64-dimension Q and key vectors, you can use like 128, 256, maybe even 1000, like 1024. If you do that, your inner product values can be arbitrarily high. So you don't want that. You want to like tame it to a like manageable value. So that is why you divide by the square root of the key vector size. So you get 14 and 12. And then once you have 14 and 12, you just do a softmax between these two. Then you have 88% and 12%. So that's how you derive the first row of the attention matrix. Well, I mean, there are only two keys, so it's only like 88% and 12% here. But that's how you do it. 88%, 12%. Now, we've dealt with X1. Now it's X2's turn to do the same thing all over again. But now we're using Q2 to ask the question, like, what's the compatibility between the first token and the second token? What's the compatibility between itself? So Q2K1 Q2, K2 and do the same thing. And that is how you can get different attention strength, even though when it is all about itself, just like what Namo has. That is how you get 50% here, but 60% here, because this is Q2, this is Q1 times K1, but this is Q2 times K2. So it can be different. All right, hopefully that helps you understand. Right, so once you have the 88%, 12%, you do a multiplication, you do a weighted sum. So your V, you do a weighted sum between 88% times V1, 12% times V2. So now you can see V2 is a little bit like way blurrier than before because this is only 12%, 12%, right? So V1, V2, you do the sum and then you, oh, sorry, not the sum. Sorry, yeah, you do the sum. So 88%, 12%, you multiply V1, V2, and then you sum it up and then you get Z1. So this part is this part. You have 2, 2, you do a weighted sum, then you get here. You have 2, 2 here, you do a weighted sum, you get this part, right? So that's Z1 and then Z2. So far, the way I talked about is that you treat one token at a time. You this thinking is the main character. You do this whole thing and then you get Z1. Now machine is the main character. X2 is the main character. You do the whole this thing and then you get Z2. Like I talked about this as if we're treating one token at a time, but that's not the case. The reason that we have the transformer is because we didn't want to treat one token at a time, just like RNN, right? We didn't want that. We wanted to have the whole process in a batch, do this in a batch manner, right? So that's what actually happens is you have all the matrix multiplications happening all at the same time. So instead of having X1 and WQ to get Q1, X2 times WQ to get Q2, you don't do that. You actually just stack them up and then just do it all at the same time to get Q1 and Q2, K1 and K2, and V1 and V2. So you have you have the Q's and K's and V's in one go. Same thing with QKV operation. Instead of having Q1 multiplied to K1 and then K2 and then doing all that and then you don't do that. You just do a matrix multiplication between all the Q's, all the K's, and then you normalize, and then you softmax, and then you multiply it to all the V's, and then you get all the Z's at the same time. So this whole thing is not doing any for loop at all. Whether you have 2 tokens, 3 tokens, 4 tokens, doesn't matter. If you have 3 tokens, you just have three rows. If you have 4 tokens, you have 4 rows. If you have 5 tokens, you have 5 rows, and that's it. If you have 3 tokens, there's 3, 3, 3, and you get 3 out. If you have 4 tokens, you have 4, 4, 4, and 4 out, right? So that's the beauty of self-attention and, consequently transformer. So you can see what's really happening here. It's this part is this part, and then you multiply it with V, and then you get all the Z1, Z2, Z3, and Z4, and so forth and so forth. Right. Any questions so far? No, okay. So we'll go straight ahead to multi-head attention. So multi-head attention is just a expansion of what we saw just now, the self-attention. We just do self-attention multiple times. So what if we used 2 attention maps instead of 1? So there's attention map here, but you could imagine another attention map here. And then if you wanted to, there could be another attention map, another. And then you just have more outputs that corresponds to each attention map. So obviously the values inside the attention map can vary between the first one, the second one, the third one, the fourth one. So they can capture different different information or different relationship between different tokens. So in the first attention layer, like I can have a compatibility with itself 50%, but in the second attention layer, it could be 90%. And the third attention layer could be 80%, right? And then correspondingly, these values will change between different outputs. So why do we do that? Actually, all right. So before we talk about the reason, the way we do about it is we have attention head 1, attention head 2. So the number of, as you increase the number of attention heads, like there's first head, second head, third head, fourth head, fifth head. As you increase the number of attention heads, you increase the number of trainable matrices. So the first head will use WQ, WKV. Oh, I forgot to mention about this. So this whole thing, these whole things are not statically determined. They're dynamically determined by Q, K, and V values, which are determined by what? Determined by these matrices, right? So this whole thing, this attention map and this and this and whole thing is controlled by only these three matrices. So when you do a backprop, they will be updated. And when you update them, when you update these parameters, their behavior, these output or these like attention matrices and whatnot, the behavior will also change. So that's what you're actually training. This the WQ, K, and V matrices. And when you have multiple heads, you use multiple WQ and V, WQ, K, V matrices. They're like the first head, there's a third head. I mean, there's a second head. If you use third head, there will be three matrices. I mean, three matrix sets. If you have four heads, you use four matrix sets and so on and so forth. So yeah, if you have two incoming tokens, if you had 8 attention heads, which was the setting from the original paper, the attention is all you need paper, they used 8 heads. So there's Z1, Z2, but there's also Z1, Z2, but this one's from the head number 1, head number 0, and all the way up to head number 7. And this also Z1, Z2, right? But they're all different. Their values will differ. So once you have different once you have like multiple heads, now you have way longer. If you concatenate them all at the same time, there's like Z0, so Z0, Z1, like Z7. If you concatenate them all at the same time, you'll get a horizontally very long vector. So, but the constraint is that your output from your self-attention has to be the same size as your input. Just like I said here, if you go all the way back here, the number of tokens that goes into the self-attention, the same number of tokens go out. And it's not just the same number of tokens, it's the same dimensionality. It has to be the same dimension. If it's 4 here, it has to be 4 here. If it was 128 here, it has to be 128 here, 120 here. So in order to respect that the constraint or condition, you have to like downsize the size of this horizontally long vector, the z vectors. So you have the output, you have one more trainable matrix here, which is horizontally really long. So these are what? This is 3 times 8 because it's a 3 dimension and there are 8 heads, so it's 24, right? So you want to change it back to 4 dimension because originally x1 and x2 were 4 dimensions. So you have 24 by 4 matrix, a trainable matrix, and then it's just like linear operation. You just linearly transform this into this form, this size, and that's it. So all in all, when you have multiple heads all acting at the same time, then this is what happens. So you have x1 and x2 going in, and then there's first head, second head, all the way to the 8th head. So there's like first route, second route, third route, fourth route, and then all the way to the 8th route. I mean 8th route. And then each route or each head produces some vectors, some z vectors, and then once you concatenate them, you need to downsize it back to the x1 x sizes. So you have the final trainable matrix WO, and then you get Z out. So this was the original implementation of transform. But these days, they don't do this. They don't actually have this long thing. What they do is instead, if you have like, for example, if this was like 1024, if this was 1024 vector, you just break it up into 8 pieces so that you don't have to deal with this kind of problem. If this was 1028 and you have 8 heads, then all you do is you just break it down into 128, 128, 128, 128. So individual these will be 128 dimension, 128 dimension. And when you concatenate them, like this, like Z1, Z2, Z3, all the way, if you concatenate them, they will be 128 times 8, which is 1024, right? So you don't have to handle this kind of problem anymore. But that's the modern implementation. The original implementation had this, but these days I don't think they do. But it's just like a design choice. The important thing is that you can have as many attention heads as you want. And if I remember correctly, I think GPT-3 had 96 heads instead of 8 heads. So we've come a long way. So why do we even need multiple heads? So this is the answer. So why do we even need like 8 heads to begin with? So if you look at this visualization, this is layer 5 of the encoder side. So assume that you've trained your encoder decoder transformer for translation, machine translation, and then there were 6 blocks on the encoder side and the 6 blocks on the decoder side. So we're looking at the encoder side, layer 5. So layer 5 is the top layer because the index starts from 0. So there's 0, 1, 2, 3, 4, 5. So this is the final layer. So this is 1, 2, 3, 4, 5, right? I mean, 0, 1, 2, 3, 4, 5. So this is the final block of the encoder. And there are 8 heads. So there are 1, 2, 3, 4, 5, 6, 7, 8 colors. And we are highlighting the second head, the orange color. So this is how, this is how the encoder, the final layer of the encoder, understands the given English tokens. So let's read this. The animal didn't cross the street because it was too tired. So, and we're highlighting the second attention head, and especially we're looking at it. So it's it is the main character. It is distributing its attention to its neighbors, including itself, right? So what's happening? So it is giving the strongest attention to the animal. Of all the English tokens, the animal is getting the strongest attention probabilities. And why is that? If you can imagine why that would be. So if you read this sentence, it's the two sentences are connected by a conjunction because. So the first sentence, the animal didn't cross the street and it was too tired. They're connected. And this it is a pronoun. And in order to properly translate this English sentence into Korean or French or whatever, you need to understand what this it means, what this pronoun means. So what you do is you do a anaphoric, I forgot the name. So anaphora resolution. There's another term called another name for anaphora resolution. I forgot. Anyways, you have to resolve the identity of this pronoun. So the identity of this pronoun is obviously the animal, right? So because the animal didn't cross the street because the animal was too tired. So that is what's happening with the second head. The second head, the second head's functionality is to resolve the identity of pronouns. That's what it is. How about the third one? How about the third head? If you highlight the third head now, it is when it is the main character, the strongest attention is given to the tired. So why would that be? So if you read this second subsentence, so this is sentence number 1, sentence number 2, connected by because. If you read the second subsentence, there's a subject and predicate. So this is the subject, this is the predicate. 그러니까 주어 서술어죠. 주어 서술어. Subject and predicate. So subject and predicate. So this third attention head is actually resolving the relationship between a subject and predicate inside a sentence, and so on and so forth. So there's like a fourth head, fifth head, first head. Okay? If you look at the attention distributions, each head is responsible for something because their attention is all different. Like this one has the strongest attention here, 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 here. I guess this not so much. I guess here, here, and here, right? So they're all different. So each attention head is handling some kind of linguistic operation or like language processing function. It's like each head is like some kind of language processing function that we don't know what it's actually doing. We can only assume what it's doing. And when you train the transformer model with enough size of like training data, then each head will have to learn something. It will have to learn some linguistic function to properly understand the given sentence and then perform some tasks such as translation, document classification. I don't know, like, question answering what give you. So that's the whole thing. Right. Before we move on to positional encoding, question from Halakim. Would be this what? Would be this attention mechanism similar to how human brain understands? Would this attention mechanism similar to how human brain understands language sequences? I'm curious how simple matrix multiplication algorithm, to put transformer simply, is able to catch the relationship between words. Very good question. And the first question, would this kind of like self-attention and hold would this be similar to how human brain processes language? And the answer is, I don't know. I guess nobody actually knows, but at least it works. And we'll actually talk about why it works when at the end of the positional encoding. We don't exactly know how humans process language. If we knew, then we wouldn't have to rely on transformer architecture. We can just build a talking machine or a language processing machine. We wouldn't have to rely on machine learning. We rely on machine learning because we don't know how to capture the patterns inside a data. That's why we just dump a whole bunch of data into the model and hope that the model figures out the pattern that we don't know. That's the whole idea behind machine learning, right? If we knew the exact rule of how data is processed, how data is generated, if we knew all the details, and if we knew the truth of the data, then we can just build the machine to do it. We don't have to train it. And I'm curious how simple matrix multiplication algorithms are able to. Well, I mean, we haven't actually talked about the rest of the architecture of transformer, but it's not just simple matrix multiplication. There is a feed-forward network. Before feed forward, everything is linear operation. If you think about the self attention that we've learned so far, it's just all matrix multiplication, matrix addition, weighted sum, and then like normalization and whatnot. They're all linear operations. There's nothing non-linear about it. But as I said in the third or the fourth class, without the non-linearity, you cannot warp or distort the hidden layer or the latent space to make it to perform your task perfectly, right? So you need a non-linearity somewhere, and that's where this comes in, the feed forward. So it's self-attention is there to figure out the relationship between all the tokens, like one another, from like token. If you're given like X number of tokens, you need to figure out the relationship between the two, and then contextualize by weight summing them, and then you massage them with some non-linearity, and then you repeat 6 times here. So that's how transformer works. Question from Kang Jian. What does the underscore after each word signify? I guess you're talking about here. Well, this is because, well, you've learned subword encoding, right? So when you use subword embedding or subword encoding, when you break down words into different parts, like you can see tired. Okay, so this is a good example. So tired is actually one word, right? But let me write it down here. Tired is one word, but when you use like some tokenizer, like byte pair encoding or sentence piece or word piece that we learned 2 classes ago, right? 2 classes ago. When you use some tokenizer, this can become, depending on which tokenizer you use, this can become tired plus D underscore. So tire, I'm assuming tire does not have a underscore, but D does, is because tire is not the end of the sentence. Tire is actually in the middle. I'm sorry, not the end of a word. Tire is actually it's not fin. Tire is like in the intermediate, or at least it hasn't finished. It's not the end of the word, but D is at the end of the word. So that is why D has underscore. Or that's what I'm assuming. So if you look at the other, actually didn't also have underscore. Okay, I'm sorry, then maybe I'm wrong. I'm assuming it has something to do with tokenizing, but I don't really know. But there's a reason that some word does not have underscore and some word does. So yeah. Question from Omite. when splitting the dimensions of input X, it looks there's no feature-wise information exchange between heads. Is there any problem just splitting? No, they are exchanging between heads. Ultimately, they are being concatenated back into one place, and then this whole thing is now a one token, which will be processed in the next encoder layer, and then the next encoder layer. So they are actually exchanging information. Hopefully that answers your question. Question from Gabriel. I guess for backpropagation, we need to optimize the weight matrices WQ, KV, and finally WO, right? Yeah, right. That is right. How do we determine the initial values of the... They're randomly initialized. As with all deep learning architectures, they're always randomly initialized. It's determined by positioning. No, but we'll talk about the positional encoding later, but they have nothing to do with positional encoding. Question from Chaeyeon. When we perform the dot product between Q and K and then divide by squared D, I don't understand why this division is if we are going to use the matrix softmax function anyway. That is a good point. Softmax function is there so that we will normalize these values to some attention distribution that sums to 1, right? But it's just a way to handle values more nicely. If we use like modern architectures like GPT, they use like 4096 dimension input, I think, or maybe even bigger, like maybe 10,000 dimension, 10K dimensional token embedding. Who knows? And then this value will be just too out of proportion, and then it won't be even if you used a softmax on top of them, their attention values will be like very different. You cannot expect a nice behavior from such a large values. So probably a nice idea to at least do some normalization beforehand. So I guess that's the idea. The final question for Pichang: can we guarantee that different multi-heads are learned with different weights? I'm guessing your question is, can we guarantee that each head will learn different functions, different linguistic functions? And the answer is no, but somehow they do. Just like if you think about the kernels or the filters of a CNN, when you use like 64 different kernels or 128 different kernels, they all focus on different things. Like first kernel focuses on like color red. The second filter focuses on like diagonal line. The third filter focuses on like the vertical line. They all learn different functions somehow, even if we don't force it, right? It's the same thing. If you use like X number of heads, they will eventually learn different functionalities. Although we don't even force it. We don't even force them to do so. So that's the beauty of machine learning. All right, so that was a lot of questions. Let's move on to positional encoding. So a transformer, as it says here, is a set encoder. I say this because if you switch places between I and like, what would happen? So let's say that your input sentence was like I going to movies termination symbol instead of I like. Let's say this is like I. Then what would happen is this obviously will be like I, and these values will change places. These values will change places. Well, we can put it here. And consequently, these values will change places, right? So that's what happens when you change the order of tokens going inside the transform, or at least the self-attention layer, right? That's what happens. But that's not what should happen. What should happen is if you think about you are a girl versus are you a girl, these two are entirely different things. This is a declaration. This is a question. This is declaring that you're a girl. You're asking if you're a girl, right? They are semantically entirely different. So their embeddings, their token embeddings output from the self-attention should also vary, but that's not what happens here. When you just switch places, their outputs also switch places, but what should happen, what should also follow is their values should also change because their order has changed. Just like the simple change, the order switch results in a completely different meaning. These values should also change, not just switching places, but the values themselves should change. But that's not what happens in transformer, and that's because it is not actually a sequence handler. It's not a sequence encoder. It's a set encoder. So you put a bunch of elements, a set of elements into the self-attention, then the self-attention will figure out the relationship between the elements inside a set, and then do a weighted sum, and then contextualize. So it's a set encoder. It's not a sequence encoder. So how do we turn a set encoder into a sequence encoder? That's where positional encoding comes in. So positional encoding is there just to say that this is the first place, this is a second token, this is a third token, fourth token, so on and so forth. So that when you change places, it will know that something different happens. Like the order actually has changed, because when you change the places between these two, this will be added with T1, this will be added with T2. Unlike here, X1 is added with T1, X2 is added with T2. So these are just there to signify or indicate the position of the tokens. So T1, T2, T3, when you add them to X1, X2, X3, their colors will slightly change. And then inside, it's the same thing. It's the self-attention, add a normalize, feed forward, and add a normalize. It's the same thing. So this is how we turn a set encoder into a sequence encoder. And you can see why transformer is such a scalable architecture. We'll talk about that later. So how do we implement a positional encoding? So positioning, in order to function as a positional indicator, there needs to be you need to meet some requirements. Like, it should output a unique encoding for each time step. Distance between two time steps should be consistent, yada, yada, yada. And but so these are a little bit too detailed. So we'll just skip to the examples. So it's the simplest way to implement a positional encoding mechanism is just by saying this is 1, 2, 3, 4, 5. You just put scalar values here, or if you don't like that, you can just have a fixed value like 1, and then just distribute it or break them down into different values corresponding to the number of tokens. So if you use the first strategy, then the problem is when you're training with 7 tokens, but you're testing with 8 tokens, you're seeing the entire new position encoding, like out of nowhere. This is like out of distribution. And same goes with the second strategy. This is good and all. Like the final token will always get 1, and the first token will always get something close to 0. But again, if you use more tokens than before, then the training, like in the test sample, there are 8 tokens, then you'll see new values here, right? So these like 2 strategies are probably not the optimal strategies to satisfy all these different conditions. So what Google engineers came up with is a pretty nice idea. So first of all, we'll talk about the binary values. So if you use binary values to indicate positions using 4 bits, so 4 bits, then the first position will be 0, 0, 0, 0. Second will be 0, 0, 0, 1. All the way to 16th value is 1, 1, 1, 1. And if you look at each color here, the first color or the first bit changes pretty frequently, like 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1. The second bit changes the values a little bit less frequently, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. The third bit a little less, even less frequently. The fourth one, and so on and so forth. So you can think of this as a frequency like this. The second one is like this. The third one is like this, and the fourth one is like this. So you can think of this as frequency, and you can generalize to real values. So this is a binary value. So binary values with 4 bits, you can only indicate up to 16 tokens, right? 16 positions. That's a waste of memory, right? Binary values are waste of space. So instead of when you generalize to real values, you're motivated by this idea of like frequency. So that is where sinusoidal functions comes in. So sinusoidal, if you look at, so this is, you're using 128 dimensions of positional encoding, because probably the input tokens were 128 dimensions, and you can signify up to 50. In this very example, you can indicate up to 50 positions or 50 tokens. So you see what's happening here. The first dimension, which is this dimension, the first dimension changes the value most frequently. And as you go up, as you increase the dimension, you can see that values are changing less frequently. Now it's like, if you look at somewhere around here, it's only like this, I guess, right? So yeah, red is -1, blue is +1. So, and if you go here to the 60th dimension, you barely even see 1. I guess this is like this, something like this, right? So that's how you use sinusoidal functions with different frequencies in each dimension to indicate different positions. And this can go on for like 50 tokens, 1,000 tokens, 1,000 tokens, 10,000 tokens, doesn't really matter. As long as you have, as long as you have sinusoidal functions, you can generalize to arbitrary number of tokens. So that's the beauty of sinusoidal functions. And the actual implementation is using cosine here and sine here, cosine here, sine here, cosine and sine here. So these pairs, the sine and cosine pair, they operate on the same frequency, and then the next two sine cosine and sine pair operates on the same frequency, same frequency, same frequency. So that's how you implement like this, right? So that's the whole idea behind sinusoidal functions. But these days, people don't always use sinusoidal functions. They also use learnable position encoding, because, as I said, the whole spirit behind using these positional encoding is just to indicate the first token and the first position and second position differs. That's the only reason we use positioning. So it could be implemented with sinusoidal functions, but you can also just use some trainable variables here. If you know that your context length is like 4K, then you just need to learn 4,000 positional embeddings, and that's it. If you know that your context length will be 8K, then you just need to train 8,000 trainable positional embeddings, and that's it. So there's not just one way to implement positional encoding. Question from Hyungwoo: why not add another dimension? Doesn't this kind of encoding destroy the original? That's actually a good question. You're gonna add, for example, first is too easy. The 30th token will receive this value, this embedding, right? So this embedding will be added to the 128 dimensional token embedding, input token embedding, and then the value will be actually different. The value will change, just like Hyunwoo said. But actually, it still works out pretty well. And people assume why that would be is because there's there's like a big, like a space here, which is just, like a storage. All the like in all the places that like all the parts that actually operates or functions as a position differentiator is this part, right? There's barely any change here. So people thought, like researchers from like 2017, 2018, they thought, oh, it's because these parts, these dimensions don't change as much as this part. So maybe the word embeddings will just put all their semantic information into this part, and then this part will only operate as a position indicator, and that's how transformer works. But that's how they assumed, or that's how they try to understand what's happening. But in reality, it just works. All right. Now to the final, well, not the final, but the comparison between RNN, CNN, and transformers. So if So RNN is basically a sequence handler, right? It's a sequence encoder inherently because you put one token at a time. So and updating the hidden layers one at a time. CNN, if you're using 1D CNN, you can also handle sequences, but it will actually focus on local dependencies more so than RNN. So because there's a filter, like if you're using like 3x1 filter, because this is a 1D CNN, if you use 3x1 filter, it'll just look at 3 tokens at a time, build up to the next layer, and then you will have like larger receptive field as you go up, right? So that's how CNN handles sequences. Transformer handles all sequences at the same time. You put all sequences at the same time. There's no local dependencies like this. There's no one at a time like this. You're just putting all the tokens in at the same time. And basically inside, it's a set encoder. Even though we use like position encoding here, inherently it's a set encoder. And when it is a set encoder, there is no implicit bias. There's no inductive bias. So out of all these architecture, transformer is the one that has the least amount of bias or assumption as to what it is handling. RNN assumes that it is handling a sequence of, so RNN assumes that we're handling a set or a data that can be represented as a sequence. CNN, if you think about 2D CNN especially, has a assumption that it is handling data that is a 2D image where nearby local dependency, like nearby pixels, are important. There's a strong implicit assumption. Transformer does not have any assumption. Transformer is a set encoder. Given a set of tokens, set of elements, it just tries to figure out the relationship between all the tokens inside a set and then just build upon that. So it has the least amount of assumption. And that is why Transformer is the most scalable architecture. You can't stack RNN like 100 times and expect it to perform well. You can't stack confident like 1,000 times or 10,000 times and assume that it'll perform well on like any given data. But Transformer, as long as you have a lot of data, you can just stack Transformer like 50 times, 100 times, 250 times, and then you can expect it'll perform well because it does not have any assumption about the given data, right? And conversely, that is why Transformer requires the largest amount of training data. RNN assumes that it is handling sequences, right? So as long as you're actually putting in sequences, RNN can handle it pretty well with small amount of training data. CNN assumes that it is handling images. So as long as you put images into the CNN model, then you can train CNN with a appropriate amount of small amount of data. But Transformer does not have any assumption. So you have to put gigantic amount of data so that Transformer can eventually figure out the hidden relationship or the hidden structure of the data eventually. So there's always a trade-off. So if you use So there's like if you use stronger assumption, you need less data. If you use less assumption, you need a lot of data. And this is it just cannot be avoided. But thankfully, we're living in the world of internet. You can scrape data, at least you can scrape videos from YouTube, text from the internet. You can scrape audio from the internet, audio from YouTube. What else can you scrape? You can scrape basically everything from the internet. And that amount of data, the internet amount of data, is enough to train Transformer so that it can understand, to simulate language, so that it can it can learn to simulate video like Sora, so that it can simulate music like Udio or like Suno or like that kind of products. All right, so hopefully that gives you some guidance, as the high level guidance as to what machine learning actually is. All right, moving on to the final. Any questions so far? All right, so no question then. Oh, that's another. Oh, actually, Chehun has. That's another question. If we replace the position encoding with learnable parameters, can you decode it back into the original tokens? Decode it back into the original tokens? I'm not sure what you mean. You mean like encoder decoder decode or um the embedding plus when it cannot be decoded. Oh, you mean like revert it back to can you like reconstruct it back to the I mean you can simply just minus the position encoding, then you'll get the original encoding, right? Yeah, okay. I think you understand what I'm saying. Okay, cool. Moving on to the sequence to sequence. So as I said, the original architecture of transformer is sequence to sequence, not just encoder. We only talked about encoder so far, but actually there's a encoder part and the decoder part. So encoder looks like this, right? We know exactly how this operates. Decoder, a single block of decoder has a little bit of difference. So it's a little bit different from the encoder. So there are, if you look at only these two, it's more or less the same, except that this is mask self-attention as opposed to this is just self-attention. Right? This is self-attention, this is this is mask self-attention, but that's the only difference between these two blocks and this block, right? But there is another thing called encoder-decoder attention. So this is here because eventually we want to translate this into some French or English or Korean tokens. So you need to plug these values, plug the information processed from the encoder side. You need to put them, send them, transfer them to the decoder somehow. So that is where encoder-decoder attention comes in. Decoder needs to be conditioned by the encoder so that it can generate words that are corresponding to this given, like, like if we're corresponding, let's say this is a French, English to French, English to French translation, then decoder needs to be conditioned by the encoder so that it can generate French words that corresponds to the English words, just like how we did with the encoder decoder from the RNN sequence to sequence. The RNN sequence to sequence, the RNN decoder is basically being conditioned by the encoder so that it can generate translation that corresponds to the input to the encoder, right? It's the same thing. It needs to be conditioned. And there are 6, well, in this case, there are only 2. There's like 1, 2, but in reality, there were 6, right? So it needs to be, the encoder information needs to be plugged into the decoder 6 times to the 6 different decoders. Why is it? Okay. And the way they do it is using encoder-decoder attention. So you can assume that mask self-attention is here because it needs to understand what it has produced so far, right? Just like how self-attention is here to understand the given input. The given input to the decoder will be the ground truth translation pair, right? This would be like French 1 and French 2. So it needs to understand that. But encoder decoder, it needs to understand what it is being fed into the encoder and what it has produced so far, so they can mix them up and then generate the next word. So we'll see one at a time. So this is okay, again, sorry. There's like a bit of going back and forth between French to English, English to French, but now it's French to English. So it's French to English. So you put the French words inside the encoder, and you have all the 6 layers, right? And then given 3 tokens, you have 3 tokens out. So this will be R1, R2, R3, and whatnot. Now we are ready to generate. You start with, first of all, you have to actually convert these R's into keys and vectors that will be used later inside the encoder-decoder attention. So there are 3 keys and 3 values because there are 1, 2, 3 tokens. So there are 3 keys, 3 values. And you start by putting the start token inside the decoder. So this is the ignition, like 시동을 거는 거죠. So this is ignition. So you put the start token inside the decoder, and then hopefully you'll get I out. So Jesuit Tudyang is I am a student in English with a termination symbol, right? So Jesuit Tudyang. So you need I as the first output, and then when you have start I, given start and I, you want M to be output, M to be produced. And with start I M, you want A to be produced and student, and then end of sentence. And that's it. That finalizes the translation process. So you have start I am a student, and each time, each token corresponding output should be I am a student, end of sentence. Just like, autoregressive language modeling, you're predicting one word, one next word at, one word ahead of time at a time, at each time, basically. Sorry about that. So one future word at a time. And so I start goes to I goes to M goes to A goes to student, and student, this is the last word. So you need to end it with the end termination symbol. So when training, you have all these ground truth French English word pair ready, and then you just put them in, and then you can just train them in a batch. You can just train them without any for loop, right? You put this all in, and then there will be like matrix multiplication, matrix operations, all the like self-attention, whatnot. There's like matrix operations, and then there will be output here. There will be like 5 output, 1, 2, 3, 4, 5 output, because there are 1, 2, 3, 4, 5 inputs, right? So there will be 5 outputs, and you have negative log likelihood for this should be I, this should be M, this should be A, this should be student, this should be end of sentence. You have 5 negative log likelihood loss terms, and then you back propagate, and that's it. So there's not a single for loop involved in this whole training process, unlike the RNN. RNN has for loop for the encoder, for loop for the decoder, even during the training process, because you have to feed one word at a time, but not transformer. You just feed all words at the same time. You do you do the self-attention here. You get 5 tokens all at the same time, and then you backpropagate, and then you just train it, and that's it. So at least training can be done without any for loop, but during testing, it's a different story. Oh, I forgot to talk about the prediction layer. Prediction layers is easy. You have one token. You have each corresponding tokens out. You just have a logit layer, and then you do softmax, and then you get the final output, right? So this I don't need to talk about, right? So I was talking about the difference between the training process and the testing process. Training process, you have all the ground truth information from the encoder side, decoder side. So no problem. You can just train it without any for loop or at all. But testing, you don't know. We can go all the way back. When it's testing time, you don't know the ground truth English sentence that corresponds to the French tense. At least you know the French tense because you have the French tense sentence that you want to translate. So this will be given as a whole, and then you can put them into the encoder without running any for loop, right? But the output, the decoder side, you don't exactly know the ground truth, what the corresponding translated English sentence will be. You have to do it one at a time. So you actually have to run for loop like this. You start with the start, and then you see, oh, I got an I. So then you put I inside the next token, just like autoregressive generation, and then see what comes out. You get M. Then you put M inside the next token. Then you see what comes out, and then you get A, you get student, you get end of sentence. So at least during testing, you have to run for loop on the decoder side. That's unavoidable. Training, you can train because you know the ground truth from the both sides, so you can train with one go without any for loop. But testing, you don't know the ground truth on this side, so you have to predict one token at a time, and henceforth you're running a for loop over the decoder. And that's exactly what's happening when you're using ChatGPT as well. In ChatGPT, you see one word at a time generated from the ChatGPT, right? So that's just unavoidable. Right. Oh, is this so? What's actually happening? Well, we forgot to talk about. Sorry, we forgot to talk about this part, encoder decoder attention. So this is to talk about that. If you think about encoder's self-attention recap, at thinking's turn, we were using Q1, and then we were doing inner product between Q1, K1, Q1, K2, and then doing normalization, and then weight sum, and then you got Z1. That's what happened in the encoder's self-attention, right? Now we are going to encoder decoder attention of the decoder side. So what's happening? Let's assume that we're predicting the very first token I. So we are given start. So we put start into the decoder, and now it's start's turn. There's no other token. It's start's turn. So we generate start's query. So there's Q1 here. And as I said, K's and V's comes from the encoder side. So there are three keys and three values. So you have Q1 that corresponds to the start token, and then you multiply Q1 with K1, this K1, K2, K3. You do an inner product between Q1. So let me just write down here Q1. Then there's K1, K2, K3. There's V1, V2, V3. So you multiply, you do an inner product between Q1, K1, Q1, K2, Q1, K3, and then you do the normalization, and then you do the softmax, and then you do the weighted sum, and then you get Z1, right? Z1. So unlike in the encoder's self-attention, everything was done internally. Like it was using K's and V's from itself, right? But in here, only the Q is from the decoder side. K's and V's are coming from the encoder side. So that's how you mix them up. And yeah, so once you have the Z1, then it'll all go all the way up to, and then it'll hopefully be able to predict the token I. And then once you have start I, then what's happening is I has Q2. Start has Q1, I becomes a Q2, and then you do the same thing, Q2, K1, K2, K2, K3, and then you do the softmax, and then you do the weight sum, and yada, 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 so on and so forth. It's the same thing all over again. And at the final step, this will be Q5. So you do an inner product between Q5, K1, K2, K3, do the same thing, normalization, softmax, weight sum, and then you get Z5, right? And then you hopefully you can predict the end of sentence. So that's what encoder decoder attention does. Right. So during training, yeah, I've talked about this. During training testing. So encoder decoder attention handles one correct. Oh, I forgot to talk about this. Again, like I said, I was depicting such as if we were handling one token at a time. Like, oh, we have Q1, so we do this. We have Q2, we do this. We don't do that. We actually inside the actual encoder decoder attention, we do the whole thing as a matrix multiplication, just like in the self-attention from the encoder side. Everything is multiplication, so we never do one thing at a time, at least during training, right? So during training, as I said, we know the GT English sentence, so it can generate all decoder output tokens at once. But during testing, we don't know GT English sentence, so we have to generate one token at a time because we don't know the total length of the output sentence. We don't know how many tokens we are going to need, right? So we are just using the previous output token as the next input, which is the autoregressive generation. So I've talked about this, right? So this is where masked self-attention comes in. So far we've covered self-attention, encoder decoder attention. We haven't talked about masked self-attention. So this will be the last section of today. The masked self-attention is there because of this difference, this discrepancy between the training phase and the testing phase. Testing phase, we don't know the whole English word. I mean, sorry, the English the translated sentence. So that's where masked self-attention comes in. So assume that we're at a place, this particular place where we already have I am, where there should be start here. We have start I am put inside the decoder, and then we are about to predict A. So we've predicted I am already. So we're about to predict A. So this is where we're at. We're about to predicting A. So currently known tokens are Jesuit étudiant. We know this because this is a French word. This is given to us. We have start I am, but let's forget about the start. We just know I am. So the currently known tokens are Jesuit étudiant and I am from the English. So Jesuit étudiant from the French side, or encoder side, I am from the English side. And the token to predict is A. So if you imagine what's happening in the self-attention layer of encoder, for example, when Sui is the main character, it can attend to itself, Je, and étudiant, no problem, because there are three tokens, so it will be a 3x3 matrix, right? So Sui can attend to everywhere. But how about M? So M becomes the Q2. I was Q1, so M becomes the Q2. So Q2, as Q2, it needs to attend to somewhere that it has produced so far. So the entire English word would be I am a student. We know this is the ground truth, I am a student. But can we allow M to attend to A and student? M can attend to itself and I, but can we allow M to attend to A and student just because we know this is the ground truth, and when we're training, we can use them? Can we allow this kind of behavior? The answer is no. The answer is no, obviously, because when testing, I am, when we are here, precisely here, about to predict A, there's no way that M can attend to A, which is in the future. During training, we knew the GT, so that we might be tempted to allow M to attend to future tokens. But when we think about the testing scenario, M will never know what will come after itself. This is unknown. So we cannot allow M to attend to future tokens even during the training phase. Even during the training phase. This is all we can allow. M can only attend to itself and I, which is the past token, previous token. We can allow this, but we cannot allow this kind of behavior because during the testing phase, this is unknown. So this is where masked self-attention comes in. So if you carefully look at the arrows here, I only attends to itself, and it can never attend to the future tokens. Never. M can only attend to itself and I. A can attend to itself and previous tokens. Student can attend to itself and A and M and N. But you see that nothing is coming in. So it has to be unidirectional. The attention has to be unidirectional. It can only go to the past. It can never go to the future. Unlike the encoder part, because encoder part, we know that regardless whether it's training phase or testing phase, the entire French words will always come in as a whole because this is a translation, right? So you can always have this full self-attention, but not the decoder side. So in order to enforce this kind of behavior, we use something called a mask. So before we do the softmax, we have QK operation, the unnormalized scalar values here, right? So this will normalize them and then turn them into probability values. But before we do that, we multiply this negative infinity mask. So this lower triangle will all be 1. The upper triangle here will be negative infinity. You multiply that, then you will get this kind of attention distribution. So I can only attend to itself. Like can only attend to itself and I. Going can attend to itself, like and I, and so on and so forth, right? So this is the unidirectional autoregressive. You can think of this as like autoregressive attention distribution because it is unidirectional. And yeah, so that is where masked self-attention comes in. So so far we've learned everything. So we've covered self-attention, masked self-attention, encoder decoder attention. And since you know all of this, you will be able to implement transformer from bottom to top, from ground up this Thursday, hopefully. I mean, in reality, you will just call a transformer function from Hugging Face. But if you're trying to do academic research on deep learning and natural language processing and whatnot, you need to understand what's exactly happening inside. And you have to be able to implement them with your own hands using very simple functions, like not just calling the APIs from the Hugging Face. And I forgot to mention this. So we will learn BERT and GPT next week. And BERT is only encoders and GPT is only decoders. So it's worth knowing both encoder and decoder at the same time. Right, so, sorry. So I think I went too far back. Yeah. Okay. So this is it. Right. So thank you very much for attending the class, and hopefully you have a clear understanding of transformer. As I said, this is probably the single most important class of this entire semester. So if you have any question, you can ask them now. Or actually, you can ask the AIT. The AIT will probably be even more knowledgeable than I am. So, but anyway, if you have question, you can ask now. I'll stick around maybe 10 seconds. I'll wait for like 10 seconds more, just in case someone's typing stuff. All right, no question then. All right, thank you guys. I'll see you guys next week. Bye-bye. 네, 감사합니다. Thank you. Bye-bye.